Today we'll have a look at the following linear algebra problem. We have to show that the set V of triples x, y, z of real numbers and that satisfy x minus 3y plus 2z equals 0 is a subspace of R3. Okay, so firstly, we can recall what are the requirements for the set V to be a subspace. So by using the subspace theorem, we can check three conditions to confirm that V is a vector space or a subspace. First condition is for the zero vector to be inside V. The second condition is for V to be closed under vector addition, and the last condition is to show V is closed under scalar multiplication. So let's have a look at the first condition. So what we'll do is let x, y, z be the zero vector in R3, which is 0, 0, 0. And now x minus 3y plus 2z is equal to 0 minus 3 times 0 plus 2 times 0. And this is equal to 0. And since it's equal to 0, it follows that the zero vector is inside V. This means the first condition is satisfied. Now we'll have a look at the second condition. So we want to prove closure under vector addition. So what we'll do is we'll consider two vectors v1 and v2, which are written as x1, y1, z1 and x2, y2, z2. And these are inside the set V. Now we'll look at the sum of the two vectors. So we'll let v3 be the sum of v1 and v2, which is going to be equal to x1 plus x2 and y1 plus y2 and z1 plus z2. Now we will check whether this vector is inside V by substituting into this formula. So what we'll do is rewrite x1 plus x2 minus 3 y1 plus y2 and plus 2 z1 plus z2. And this is by substituting the coordinates into this formula. Now we can rewrite this as the sum of x1 minus 3y plus 3y1 plus z2z1 and plus x2 minus 3y2 plus 2z2. This is just rearranging this sum. And now, since v1 and v2 are inside V, we know these two things must equal 0 because this is the condition for v1 and v2 to be inside V. So now we must have two different zeros here, and 0 plus 0 gives us 0. So this whole expression over here is equal to 0. And since the whole expression is equal to 0, it follows V3 is inside V as well. So the closure under addition condition is satisfied. So condition 2 is satisfied. Now we'll have a look at the final condition, which is closure under scalar multiplication. Now let V be inside the set capital V, where little v is equal to x, y, z. And now we will pick a scalar lambda which is inside the reals, and we find lambda v is equal to lambda x, lambda y and lambda z. And now we want to check if lambda v is also inside the capital V. So we will again substitute into the formula from earlier, which is x minus 3y plus 2z equals 0. So we'll check if this condition is satisfied again. So we have lambda x minus 3 lambda y plus 2 lambda z, and this we can factor out the lambda, and we get lambda times x minus 3y plus 2z. But since lowercase v is inside capital V, we know x minus 3y plus 2z must be 0. So we're going to have lambda times 0. and lambda times 0 is 0, which means this expression over here is equal to 0, and therefore lambda x is also inside capital V. This means the final condition of closure under scalar multiplication is also satisfied, and since all the three conditions are satisfied, we can use a subspace theorem to show capital V is indeed a subspace of R3. Okay, so that concludes the proof of capital V being a subspace. So hope you enjoyed this video. Thanks for watching, and I'll see you next time.